With impacts of AMR being felt all across the globe, many people are working tirelessly to find ways to control and contain the spread before it becomes an even larger issue.
For instance, we know that where humans and animals exist, you will also find their fecal waste containing billions of bacteria, and as a result, antibiotic resistance. Countless engineers, scientists, and public health professionals have spent their lives working towards creating safely managed sanitation services to separate humans and animals from their fecal waste, which would protect both humans and the environment.
To help conceptualize the main pathways of fecal waste exposures, public health scientists have used the F diagram: fluids, fingers, flies, fields, floors, and food. There are three types of ways we can intervene and interrupt these pathways. First, through improved sanitations, such as piped sewerage and or off-site treatment. Secondly, clean drinking water in underground pipes or from uncontaminated well sources. And lastly, behavioral hygiene interventions like hand washing and food preparation education. Since antibiotic resistance mainly involves the relationship between humans, animals, and the environment, public health leaders have advocated for a One Health approach to understand and reduce the spread of resistant features. Simply put, a One Health approach is a collaborative effort of multiple disciplines that addresses the AMR threat as a whole, aimed at providing optimal health for people, animals, and the environment through policy, research, education, and practice.
While raw fecal waste in the environment is arguably the worst case scenario, even our efforts to keep that from happening don't always have the intended outcomes. Here in the US, we don't often think about what happens after we flush the toilet, but it turns out that it does not magically disappear. Human wastewater is commonly treated using conventional wastewater treatment plants that are designed to remove large solid particles and break down organic matter. They combine physical, biological, and chemical treatments in three different phases: primary, secondary, and tertiary treatment. In primary treatment, wastewater undergoes physical sedimentation, where the larger particles sink to the bottom in the remaining liquid and smaller particles continue onto secondary treatment. In secondary treatment, we use microorganisms to break down dissolved pollutants. Finally, in tertiary treatment, the water is disinfected and then released into surface waters such as rivers and lakes. We refer to this final treated product as effluent.
While conventional wastewater treatment has been essential for human and environmental health, it is unfortunately not as reliable as we would like. Conventional treatment produces large amounts of fecal sludge that is removed during primary and secondary treatment, and inside this fecal sludge is a huge buildup of antibiotic-resistant genes, antibiotic-resistant bacteria, and antibiotic residues, which makes it a strong source of antimicrobial resistance. Despite this, it is often used as a fertilizer, which then spreads that antimicrobial resistance into the environment. In most cases, the conventional wastewater treatment process does not remove all antibiotic-resistant bacteria or antibiotic residues by the time the effluent enters the environment, and it is not set up at all to remove any antibiotic-resistant genes. These pollutants then re-enter the environment, spreading resistance to environmental bacteria. For example, let's talk about ciprofloxacin, a commonly prescribed antibiotic to treat a variety of bacterial infections. Wastewater treatment removes up to 90% of ciprofloxacin from the water that enters the treatment plant. The removed portion of the compound compiles in the sewage sludge, where microorganisms are largely ineffective at breaking it down. If the sludge is later used in crop fields, the ciprofloxacin molecule can remain intact for more than 90 days in the soil. This is a perfect recipe for selective pressure to take place and lead to acquired resistance in environmental bacteria.
So despite the fact that conventional wastewater treatment commonly removes most of the bacteria present in wastewater, its effectiveness regarding the removal of antibiotic resistance genes, or ARGs, has been less consistent. In fact, wastewater treatment plants have been discovered to harbor a wide variety of ARGs within the water and the sludge, increasing the chances of genetic transfer between bacteria to occur, which has concerned many public health agencies due to its potential environmental effects.
And unfortunately, while high-income countries such as the United States can treat around 70% of generated wastewater, lower-income countries are only able to treat around 30% or even less than that. And as global populations continue to rise and more people are moving into cities, Existing sanitation infrastructure cannot handle their growing capacity.
As we can see, while we have made great efforts to regulate human wastewaters, we haven't quite reached its full potential. For example, we know that on-site pharmaceutical waste treatment is essential before it is released into the sewer system, and there are new technologies and innovations happening in this field constantly, such as membrane filtration systems, UV radiation, and ozonation. But right now, many of these are costly and not given the priority that they deserve.
What this means is that we have to continuously be looking for new and innovative ways to combat the threat. Otherwise, the resistance will keep growing and getting worse. So, how can we accomplish this?
It starts with future leaders and professionals, with a higher emphasis on controlling AMR and utilizing a comprehensive method such as the One Health approach. Researchers and scientists can continue to make improvements to current treatments, as well as discover more sustainable practices.
But it doesn't stop with public health officials. Experts in areas such as policy, economics, and education can do more to change our current mindset, whether through raising public awareness about antibiotics or crafting new guidelines to follow.
And when we combine these practices with an effort to reduce overall antibiotic consumption, then we may have just what we need to keep our planet safe.